Okay, in this video I'm going to do another Taylor series. And so this time our function is f of x equals 1 over x squared, and it is centered at x equals 1. Or in other words, a is equal to 1. So as I stated in my last video, what I like to do is start by writing out the function, 1 over x squared, and then evaluate that at a. So f of 1 is 1. Take the second derivative, the first derivative. The first derivative of 1 over x squared is negative 2 over x cubed. Evaluating that at 1, we get negative 2. The second derivative, 6 over x to the fourth. Evaluating that at 1, we get 6. Third derivative, negative 24 over x to the fifth. Evaluating that at 1, we get negative 24. Now, putting that together into my little formula, the first thing we want is f of a. And so f of a is just 1. The next term is f prime of a. So we have f prime of a times x minus a. So f prime of a is negative 2. And a, of course, is 1. So we get x minus 1. And that's it. The third term is going to be f double prime of a times x minus a squared over 2 factorial. And so f double prime of a is 6 times x minus 2 squared over 2 factorial. And then f triple prime of a, which is negative 24, times x minus 1 cubed over 3 factorial. And now you can simplify that a little bit. 2 factorial is simply 2. It cancels with the 6. We get 3. 3 factorial is 3 times 2, which is 6, which cancels with the 24 4 times. And so our simplified polynomial becomes this. That is our polynomial. Our Taylor polynomial centered at x equals 1 for the function 1 over x squared. So what we are doing right now is we are creating Taylor polynomials that represent these functions. Next up, in exercise 2, we want to expand this just a little bit. We want to write out the first 4 terms of the Maclaurin polynomial. So remember, the Maclaurin polynomial means that we are centered at a equals 0. A Maclaurin polynomial, once again, is a Taylor polynomial specifically centered at a equals 0. Then what we want to do is we want to find the formula for that Maclaurin polynomial, and that will be the Maclaurin series. And then I'm going to leave it up to you to use Desmos to graph the polynomial and compare it to the function. I've already done a video on this that I hope you take a look at. So first of all, f of x is e to the x. So evaluating that at 0, we get 1. This is an easy one to do because the derivative of e to the x is always e to the x. F prime of 0 is 1. F double prime, f triple prime, and they're all equal to 1. Then I wrote out my formula here for the Taylor polynomial. And technically speaking, for a Maclaurin polynomial, I don't need to write the x minus a because a is 0. I could just write x, but I always just write x minus a. And so then f of a was 1. Boom. F prime of a is 1 times x minus a, which is x minus 0, which is x. So 1 times x is x. And then f double prime of a is 1 times x minus 0 squared, or x squared over 2 factorial, and then x cubed over 3 factorial. And so from this now, what we want to do is we want to determine the general formula for this polynomial. And so looking at these, sometimes it's easiest if you just skip the first term. Ignore the 1. Start with the x. And here what I have is x to the first over 1 factorial, x squared over 2 factorial, x cubed over 3 factorial. So if we start with n equals 0, this would be my 0 term, my first term, my second term, my third term. And so we can see that x is raised to the n power, and it's being divided by n factorial. And that gives us the formula for the power series for e to the x. This power series, which is specifically a Taylor series. So what we've done here is we have created a power series that represents e to the x. Okay, now, again, just a little note, I've already explained this, but a Maclaurin series is a specific type of Taylor series, so it's not improper to call a Maclaurin series a Taylor series. So all Maclaurin series are Taylor series, but not all Taylor series are Maclaurin series. The last two problems we want to do are sine and cosine, another couple of common functions that we're all familiar with. And we want to find a Taylor series that represents the sine of x. So f of x is equal to the sine of x. So there's f of sine of x. The sine of 0 is 0. F prime of x is cosine. Evaluating at 0, we get 1. Second derivative is negative sine of x. Evaluating that at 0, we get 0. Third derivative is negative cosine. Evaluating at 0, we get negative 1. Plugging it into the formula, we have f of a is 0. F prime of a times x minus a is 1x. And then f double prime, all of this becomes 0. F triple prime of a times x minus a cubed over 3 factorial becomes this. So now, originally, this is my n equals 0 term, the first term, the second term, and third term, but we're going to eliminate the terms with the zeros in them to simplify this. And so what we end up with is something in green. We end up with this. So we want to look for a pattern here. And so this particular pattern, this is going to start at n equals 0. So this is n equals 0, n equals 1, n equals 2, n equals 3, n equals 4. And so you want to look for the relationship between the powers 3, 5, 7, and 9 and the n number. Well, as it turns out, these are increasing in an arithmetic sequence. 3, 5, 7, 9, there's a common difference. It happens to be an arithmetic sequence, and that sequence is 2n plus 1. So when n is 1, we get 2 times 1 is 2 plus 3, we get to the third power. When n is 2, we get 2 times 2 is 4 plus 1 is to the fifth power. And so that works. And it just so happens that the factorial in the denominator is going to be exactly the same. So what we have here then is we have the sine of x is equal to the Taylor series, or the Maclaurin series, from n equals 0 to infinity of negative 1 to the n, x to the 2n plus 1 over 2n plus 1 factorial. So this is the power series representation of the sine of x. So now we have a power series representation for the common function e to the x and for the common function sine of x. And likewise, the last one we want to do is another one, is the cosine of x. And so you should be able to go through and do this one fairly quickly. We want f of x is cosine of x, f of 0 is 1. The derivative is negative sine, f prime of 0 is 1. We get our derivatives and we evaluate them. And then we put them into our little formula and we get this. Every other term is going to be a 0. And so getting rid of the terms with the zeros and then approximating, so that doesn't give us much, just give us 1 minus x squared over 2 factorial plus x to the fourth over 4 factorial. But just like with the sine, you can pretty much see what the pattern is and just keep adding the terms on, which is what I did here. So we see that we have an x squared 2 factorial, then an x to the 4th 4 factorial. The next term is going to be x to the 6th 6 factorial, x to the 8th 8 factorial. The other thing is that the terms are alternating. Positive, negative, positive, negative, positive, negative. So when we create our Maclaurin series for cosine of x, we're going to have a -1 to the n in it, just like with sine. And again, we have an arithmetic sequence, which happens to be 2n. I actually made a boo-boo on this. This should be 2n and 2n factorial. I don't know what happened to my 2. The power series representation, the Maclaurin series representation for the cosine of x is -1 to the n times x to the 2n all over 2n factorial. Now, if you're still a little bit confused about what do we actually mean by a power series representation of the cosine of x, what exactly does that mean? Well, again, I did a video on the sine of x using the Maclaurin polynomial. And as we increase the number of terms in our polynomial, the graph of the Taylor polynomial approximates the graph of the cosine of x. And so as we go towards infinity, as the Maclaurin polynomial has an infinite number of terms, then the graph of this power series is exactly the graph of cosine of x, which is essentially saying that the power series is equal to cosine of x. All righty, so that's it for this video. I hope you enjoyed it.